Greetings, everyone. Professor Simon here to talk to you about relations and functions. So let's start with relations. In a word definition, a relation is meant to be an input-output machine in mathematical form. Okay? The way we break it down is you'll have a big set, and inside of that set is just a group of points, right? X, Y, X, Y, X, Y. It's a set of pairs, right? Not the yummy kind, no, the graphing kind, right? So I have a point, I have a point, I have a point, I have a point. Each point is an X and Y, and it's really meant to be individual little relationships. This X is related to this Y, this X is related to that Y, that X is related to this Y over here, so on and so on. That's what a relation is, okay? It's a grouping of all these little relationships. Now, when you put these together, hopefully they form some sort of pattern that goes along with whatever problem you're working. But for now, we're just talking about the simple mechanics of this, okay? So, a relation is just going to be these points. And what's really going on is we have the set of input numbers and we have the set of output numbers. But the relation itself is the collection of the relationships, not the numbers, okay? But the collection of the input numbers is called the domain, and the collection of the output numbers is called the range. And when you have a discrete relation, as what this is, discrete just means countable, right? I can see it has 4 points. Then it's easy to tell the domain and range right away. You just list the x's for the domain, the y's for the range, okay? So the actual relation, though, you'll notice I have it labeled as the arrows themselves. That's really the relation, the connection between these values, okay? So then you can see relations that are in this kind of format. Sometimes you'll see those same kind of relations in a graphing format where, since I only have 4 ordered pairs, I only have 4 points. And then eventually, more generically, our relations are going to be given with equations, and those equations give us graphs that are an infinite number of points. Okay, that's the only way that we can do an infinite number of points in a relation, because I can't list an infinite number of points individually. I have to use equations for patterns, but that's still a relation. Okay, now to put the next twist on this, a special kind of relation, which is all of the relations you'll really study throughout all of algebra, are functions. Functions have one extra little rule tacked on. They're still relations, input-output machines, okay? X's and Y's paired together. But all of the input values, domain values, you're going to be using X's for those, okay? All of those are restricted to one pair. You can only use an X value one time in a pair in your relation, and then it's a function. If you violate even one time, it's not a function, okay? So I have some examples here on both sides of the board of things that are and things that are not functions, okay? So first, as you can see I've written right here, this A right here is a function. Look at all of the X values, 2, -3, 4, 7, right? Notice each one only has one pair coming off of it, right? One arrow. Each one is restricted to one use. It's a function. It doesn't matter, by the way. Notice the 5 is used twice as an output. That's okay. That's not part of the restriction. Inputs are restricted, not outputs. Okay? Here, B is not a function because I can see the number 1 has been paired in 2 different pairs. Right? The one's cheating. No, no good. That's not a function. Okay? It's like a drink machine. If you come up to the drink machine, you got to give it an input, right? Push the button. That's the input. Push the button, and then it gives you an output, the drink, right? But if some days you push the Coke button and it gives you a Coke, but other days you push the Coke button and it gives you a Sprite, there's something wrong with that. It's not functioning, right? Every time you hit the Coke button, it should only be paired to one output. Coke button, Coke drink. It should be that way every time. And you see something that's mapped more than once is not reliable. If I feed this B relation a 1 as an input, right, because that's what this is, don't forget, input-output machine. If I feed it a 1, it should give me the 4 every time to be reliable. But B right here, sometimes he may choose to give you the -3 when you give him the 1 sometimes. That's not reliable. And in math, all of our proofs and everything else, everything has to be reliable. So things that have an x value, a domain value that's mapped more than once, not a function, not something that we can rely on. Okay? Some other examples here. This guy that I have down here in graph form. Notice I can look at it vertically. See, the x value is -8. This x value is -4 on the axis. This value would have been 2 on the x-axis. This value would have been +8 on the x-axis. So if I go down the x-axis, each of the x's that I am using only has 1 point above or below it, right? Same thing over here. This guy's in an equation, but every time I pick an x, like let's say I pick -2, right? If I go look at the curve, -2 only has 1 point above it, right? So it's only used one time. And the same thing would be true for any x value. You go anywhere along the x-axis, pick a number, and you see it was only in line vertically with 1 point. Okay? So as you can see, there's ways that I can tell right away from discrete by looking at the numbers. And then there's also a way graphically that you can tell if something's a function by looking vertically and making sure no points, no x values are sharing between 2 points. That's called the vertical line test. And here's a couple of examples that fail it. Look, these two are not functions because they don't pass that vertical line test. In other words, if you take any vertical line, even one, just one vertical line, right? And that vertical line, they have the same x value, like these 2 points right here, or even better, these two are both on the y-axis. Look, that's a vertical line. It only takes one vertical line hitting 2 points of your graph. Automatic fail as soon as just one vertical line. So a function, right, one of these guys, is a relation that passes every single vertical line, right? Every single vertical line only hits once. Vertical line, run your pencil across it this way, right? Every single one of them hits it once. So those are functions. Notice a circle is not a function. It only takes one vertical line hitting it twice to make it not a function. That's the same idea as having an x value that's mapped more than once, right? A vertical line hits an x value, and those 2 points are both using that same x value. So one vertical line fails it. Continuing on graphs, you may have to look at one of these types of relations and have to decide on what the domain and range are, okay? They don't have to be functions, by the way, for you to be able to give a domain and range. It's just that functions are going to be what we'll mostly study in algebra, but relations still have input and outputs, even if they're not functions. So you still have a domain and a range, okay? So here we go. When you're reading domain and range, you have to remember what kind of sets you're doing. Domain is supposed to be inputs, and we've set forth that our inputs are x's. So I'm going to read along the x-axis from left to right and see where the values are being used, okay? Don't let the up and down information get confused, because bottom to top is range. For domain, I'm going to go left to right, and I'm going to stay focused on the x-axis, just looking at the x numbers to do this, okay? So right here, look, starting on the left, there's nothing over here, nothing, because there's no graph, right? Nothing, focusing on the axis, and then boom, I have a first point, well, a hole, but still first a starting point at -5. So my domain, what I do is I list -5. I'm going to use interval notation here, okay? Let me finish it up. From left to right, -5 to 6 here. Notice 6, it stops, right? And then there's no more graph on this side of it. So from left to right, -5 went to 6, okay? -5 was not actually used anywhere, right? It's open. So I put a parentheses. And then 6 was used, so I put a bracket, okay? Don't forget, that's interval notation. And the whole point of interval notation is to list out sections of things, right? So all you have to give is a beginning number, comma, an ending number, and then you just need to give parentheses or brackets, whether it's included or not. Brackets are included, parentheses are not included. And you put one on each side, right? So here my domain goes from -5 to 6. Whereas my range, remember range, again, you're going to focus on just the axis that you're questioning. So here that's the y values, right? So from bottom to top, I'm only going to look at this axis. Don't look everywhere else. Look here. These are the numbers. It starts at -4, and it goes and it goes and it goes, right? Stops at 3. There's no other y values above that. Okay? So my range is -4 to 3. And again, these don't have to be in the same, parentheses bracket order. Okay? It just so happens that -4 is the y value that's not being used, but it is a starting point, right? So that's why I have to list it like that. Okay? Let's hear, right? There's no numbers on there. I can still do a domain and range though, because I know where the axes are, right? From left to right, you have to remember that these arrows usually have more than one meaning, okay? Arrows like these, they don't just point in one direction, okay? This one's pointing down, sure, but think about it. If this is a function, and usually they are, it also has got to slightly get wider as this goes. So technically this arrow is pointing down, but it's also pointing a little bit left. And the left part is what I'm interested in when I'm looking at what is my domain, the left part. Since it's an arrow, it goes forever to the left, -infinity. Okay? And then notice here, sure, it's pointing down, but it's also got to be pointing just a little bit to the right. Yeah? There are no breaks anywhere in here. That's important. So from left to right, if you're looking at the axis like you're supposed to, used, goes forever to the right, goes to infinity. All good. Range. Well, remember, range is the y-axis, right? Bottom, look, down forever, down forever. My bottom is going to be -infinity. To top, it caps right here. There's no graph up here. So for my y-axis, stops right there, right? That's the axis. That's y equals 0. Notice those point that y value is actually used. It's actually used more than once. That's okay, it's a y value. Range can do that. Since it's used in points, I actually bracket it. Okay? Next example here, it's not a function. That's okay. It still has input and output numbers. Okay? So domain, range, bottom to top is my range. Domain is left to right. I just need some numbers in there. Well, it hits the axis here and here, yeah? And the radius of this circle is 5. So technically, shouldn't it also be 5 here? It should be 5 here. It should be 5 there also, right? It's a circle. It's 5 in every direction. Well, all right. So that means my domain is going to go from -10 to 0, right? Because it starts over here, hits over there. And then my range from bottom to top, it starts at 0 and goes up to 5 plus 5 goes up to 10. Right? All right. One more. Domain. Range. For doing domain, we got to go left to right. Don't forget this arrow right here. It points both down and it points left. The left part I need for the domain. It's going to be negative infinity. It doesn't break anywhere, right? So it's all smooth, all connected. All of these x values are going to be used, and then boom, I hit a dot. It just stops. So my last x value, right, if you extend your axis here, the x value right there is 57, it says, according to this point. So my last x value in the domain is 57. And I'm going to put a bracket on it because it's a solid dot. Okay, now the range. Bottom to top. Well, don't let this point throw you off. This side goes down forever. So that point doesn't even matter to the range because the bottom is going to be negative infinity. Right? And then it passes that point up. Where's the top? The top value that's used right there is 13. And should I bracket or parentheses? Is that 13 actually in a point? It sure is. It's in that top point right here, right? So bracket. To finish up this introduction on functions, you also need to know the ins and outs of the functions that we use most of the time, which are going to be functions written as equations. And that's because equations are the only way that I can talk about an infinite set of points in a relation. Okay? So of course we need to know right away, if we look at an equation, if it's a function or not. Okay? And it's usually pretty straightforward. The idea is, if you can get the output variable isolated without any double function happening on the other side of the equation. And to be honest, at this point, most of you the only duality or double function that you would know about is the plus and minus symbol. Okay, so I have a couple of examples here for you to see. And we're going to label them as functions or not. And then we need to talk about their domains too. Okay? So, let's start with the first one here. Y equals negative x plus 1, right? We're going to look at that one first. Y is by itself. The output variable is isolated. And there's no double answers over here. If I plug in one value of x, I do a calculation, I get one value of y. So every x is paired one time, right? So this is a function. Okay. Next, x is isolated. X is not the output variable, right? Y is. There's no y in the equation, okay? This is not a function. Okay? If you can't get y by itself, then it's not going to be a function. Think about it. I can only pick a single x value, negative 5, and that would apply now to all the y values. And if you think back to your section on graphing lines, remember, x equals a number is actually the graph of a vertical line. Definitely wouldn't pass the vertical line test because it is himself a vertical line. Okay? Y equals 2. That one's okay. Y is isolated, and any x that I pick, I get an output for. And it's never more than one. So yes, this is definitely a function. Okay. Next one down right here. Y is already by itself. If I plug in a single x, I only get one answer. There's no plus and minus or anything. So this is also a function. Right? Pretty straightforward when the y is already solved for, right? So now let's talk about these two. Right? If I solve for y in this guy right here, notice what I have to do is I'm going to subtract the 2 this way, and I'm going to add the y squared this way. So what I have is x minus 2 equals y squared, right? I'm adding y squared, and I'm subtracting 2. Then to get rid of the squared, because I got to get y by itself, I'm going to have to square root. Well, that's fine and dandy for equations, but whenever you're doing this in general, don't forget, a square root brings his buddies with him, plus and minus, right? Because you have to answer that question generically. Well, if I plug in a single x, I'm going to get two answers, a positive one and a negative one. So this guy is not a function. Right? Here's a little call sign for you. If you see a y with a squared on it, the same problem is going to happen every time. Okay? Probably not going to be a function. Let's solve this guy. Right here, if I subtract the 3x squared, then I divide by 2 everywhere. I have y by itself. And I notice that if I plug in a single x, right? I square it, I multiply it by negative 3/2, I add 36. There's no double calculations there. One x, one calculation, single answer. So therefore, this is a function. Okay? So you should be able to look at an equation and determine if it's a function or not. And if all else fails, solve for y, see if you get that duality, which really, as you can see, only happens in the cases where you have things like y squared and the things where y is not even in the equation, right? Okay, so let's also talk about how you would find the domain on something like this, because we're not looking at a graph and the points themselves are not listed out, so you can't just read them. It comes back to the domain is supposed to be a list of what x's you can use. When I was doing one of those original ones with the braces and the sets of pairs, the points you can use are physically shown to you, right? In an equation, you're meant to assume that you can really use anything for x unless it causes some sort of malfunction. So think of this like I'm bringing a new machine, input, output machine, don't forget. I'm bringing a new machine to the boss or to the customer, and you have to give a set of instructions, right? That's what the domain's going to be. The set of instructions for the values that you should use and the values that you shouldn't. Now, most of the time on these equations, domain's going to be pretty much every number you can imagine. There's only a few exceptions, okay? Let's take a look at this first one right here. Y equals negative x plus 1. Think of any number that I could plug in for x that would cause a malfunction. And by malfunction, I mean division by 0. Big no-no, right? Can't divide by 0. Square root of a negative number, cause imaginaries. We don't graph those either. Those are the two big ones for now. Later on in algebra, you'll also learn about logarithms that can't handle negatives and zeros. But for now, the two things you should be looking for in finding the domain on this: does it have a division by 0? Does it have a square root of a negative? I don't see any divisions or square roots here. I could take any number and opposite it, right? That's the negative, and then add it to 1. I can do those to any number. There is not a single number where those two actions would cause a problem. So the domain here is all numbers. I'm going to just put negative infinity to infinity, right? The whole x-axis. Okay, let's just do the function ones because really the equations, the other ones, we're not going to worry about. Here, this function right here, it doesn't even have an x. No square roots, no divisions. Domain, negative infinity to infinity, right? It's never going to have any problems. Y is 2. You can pick different x values all you want. It's always going to give 2 as an output. Okay? And then this guy right here, we hit our first bump. Look, if I plug in what number, the bottom will be 0. What number could I put there? 2, right? 2 minus 2 is 0. Well, that would be 1 divided by 0. When x is 2, this thing causes division by 0. Well, then I better not let x be 2, right? So here, there's two ways I can list this domain. Remember, it's a set of instructions. You could just warn the user, hey, don't let x be 2. X can't be 2. But in all honesty, we like to give our domains in interval notations because we want to say what x can be, not what it can't. It can be anything else, right? This implies that it just can't be 2, but it can be anything else. So my domain is actually negative infinity all the way up to 2, but don't include the 2. And then also it can be everything starting at 2 all the way to the right, right? So imagine your x-axis and 2 is right there in the middle somewhere. I can be everything on the left of 2. I can be everything on the right of 2. That's okay. Okay? But I just can't be 2 itself, which is why there's no brackets there. And then to finalize it, you just put a union symbol between them to show that they're united in one answer set. Okay? This one right here. Look at this rearranged version. I don't see any square roots. There's a square. That's okay. And I don't see any divisions by variables. Be careful. I know there's a division right there in that fraction, but it's always 2. That denominator is never 0, right? It's not like this one over here where there's a variable in the division. It's just division by 2. No big deal. So the domain here, again, is all numbers. Okay? The two things you're looking for, division by 0, square roots and negatives. That's the ones that are really going to kill your domain. Okay? One other little thing. Whenever we have a function, we like to get y by itself. That tells us that it's a function. But what that also does is it gives us what we call a function notation for our equations. Okay? In other words, my output variable, the thing that you're expecting to get back in this relationship, is a result of, is equal to, some calculation of the input. Okay? So for example, this is a functional setup right here. Y equals 3x squared plus 1. Okay? Y, the output, is the result of a calculation involving the input. You feed an input, it does a calculation, there's your output. That's why we like to think of it that way, as functional formation. So to take it the last step in that structure, I generalize my output into something that has a name and an input listing. Okay? So right here, this F, whatever it is a name. Okay? I could use G, H, A, stickman, whatever. It's just the name in case you have more than one function in your problem. Okay? And next, the X right here. This is going to be your input value. It is not a multiplication. It is not something that I have to divide to solve for F either. Okay? The parentheses here is literally just extra information so that you can stay organized when you're dealing with a function. It's just extra info. It's like a little reminder. It's the parrot on your shoulder here. Rock, X was 2, rock, right? Repeats over and over again. That's all it is. It's not even really there, okay? It's just extra information. Notice in the original setup here, I have the name of F, and it's telling me, hey, when your input is X, you take X and square it, multiply by 3, and add 1. So it's a generic definition. For any input X, this is what you do with it. Okay, so F of 1, what does that mean? Look at the function named F. There he is. Put 1 in for X. So 3, 1 squared plus 1. Right? Okay, well 3 times 1 squared is 1 times 3 is 3 plus 1 is 4. So F of 1 is 4. Okay, notice I did not multiply or divide by the 1. It is information. It's not an actual calculation. That's just information. F of negative 3. Find F. There he is. Put negative 3 in for x. Okay. 3, negative 3 squared plus 1. Negative 3 squared is 9. Times 3 is 27. Plus 1 is 28. Therefore, f of negative 3 is 28. Lastly, find function f. There he is. Put 0 in for x. All right. 3 times 0 squared plus 1. 0 squared is 0. Times 3 is still 0. Plus 1 is 1. Okay? Something else you should realize about this is it's not just a way of rewriting your equation. It's also about a way of communicating something that this function has, or some of the relationships that this function contains, right? This is telling me that if I feed the function f the number 1, if I give him the input, he outputs a 4. If I give him a negative 3, he outputs a 28. If I give him a 0, he outputs a 1. Input, output. That's what functions and relations do. Okay? Also, though, don't forget, if I were graphing this, on the graph of f, the point 1, 4, because that's an x, that's a y. The point negative 3, 28, and the point 0, 1. Right? Also, if you have something like this, don't forget, a point like 0, 1 is an intercept, because one of my coordinates is 0. That would be the y-intercept of this one. Okay? Well, I hope this helps you in your introduction to functions.